Greetings, everybody. These are going to be the last couple of lectures for this semester. This is the last couple of topics from Chapter 10, dealing with rotational kinetic energy and then angular momentum. And this video will cover rotational kinetic energy, and then the last one will be, last one or two will be angular momentum. Remember, kinetic energy is the energy due to motion. Well, if something's rotating, it's moving. So it's going to have kinetic energy. Well, we call this rotation, we call this kinetic energy rotational kinetic energy, or Ke, with the subscript ROT for rotational. So rotational kinetic energy, it's the energy due to rotational motion. Every rotating object has rotational kinetic energy. And remember, if it's rotating with some angular speed, omega. And it has a moment of inertia, I. Well, rotational kinetic energy is simply 1/2 I omega squared. Now, remember, there's also linear or translational kinetic energy. Translational, linear mean the same thing. Well, the linear kinetic energy of a moving object is 1/2 mv squared. So your system, which we'll look at in this figure here, a system can have linear and or rotational kinetic energy. And again, we're going to solve problems. We can solve them using Newton's second law for rotation and Newton's second law in, for example, the y direction. Or, likewise, what we did in chapter 7, we can use what's called an energy approach, using conservation of energy, which sometimes is a little bit easier. Well, let's look at what we mean by that a system can have linear and or rotational kinetic energy. Well, let's look at this system here. You've got two masses, M1 and M2, and they're connected by a light string, and this light string passes over a frictionless pulley, and this pulley is fixed to rotate about an axis that passes through the center. It has a radius of r. Now, we're just calling the moment of inertia of the pulley I. In other words, unless I tell you otherwise, we can't assume that pulley is a uniform disk. It may or may not be, it isn't, because you see I have a little indented surface here. So we're just going to call the moment of inertia I. But the disk is, the pulley is still not disk, pulley. But the pulley is pivoted. There's a frictionless pivot through its center. Well, what happens is the objects are released from rest when they're separated by a distance of 2h. And I just said M1 is greater than M2. And so we have M1 connected to M2 via this light string that passes over a frictionless pulley. The frictionless pulley has a moment of inertia I, and it has a radius of r, and it's pivoted. There's a frictionless pivot that passes right through the center of the pulley. But we're not assuming, we cannot assume that the pulley is a uniform disk. If you can assume that, I would tell you. But in this case, we're just calling the moment of inertia I. Systems released from rest when M1 is at a distance of 2h above M2. Well, why does this system include rotational kinetic energy? Because when you release M1 from rest, M1 will move downward with a speed of v. And then look in this next figure. M2 will move up with that same speed v. So M1 and M2 have linear kinetic energy. 1/2 M1 v squared and 1/2 M2 v squared. Those are the respective kinetic energies of M1 and M2. Well, when they're released, and in this case, the pulley's going to rotate. The pulley's going to rotate with some angular speed omega, as shown here. And so the pulley is going to have a rotational kinetic energy, 1/2 I omega squared. So in other words, the system, and again, we don't want to overthink when we talk about the system. The system is simply equal to M1, M2, and the pulley. When the system is released from rest, M1 will move downward with the speed of v. M2 will move upward with the same speed v. the pulley will rotate with some angular speed omega. And the pulley has a moment of inertia I, and it has a radius of r, and it's pivoted about an axis that passes right through the center. Well, so what do I want? I want to know the translational speeds of the object. I want to know what is the speed at the point where they pass each other. And then I want to know what is the angular speed omega of the pulley at that same instant. Okay, so what happens is system is at rest. M1 is at a height of 2h above M2. Released from rest, M2 moves down with the speed of v. M2 moves up with the speed of v. When they pass each other, right here at this dotted line, when they pass each other, I want to know what is v and what is omega. Well, in my solution, I'm going to set the reference point. Remember, reference point only refers to gravitational potential energy. I can't stress that enough. By now you should know, when I say reference point, it's understood that's the point where the gravitational PE is 0. Well, I'm going to set the point when M1 and M2 pass each other, when they're at the same height. I'm going to set that, that's my reference point. That's where the PE is 0. Okay? So remember, all right? So let me apply conservation of energy. Initial potential plus initial kinetic equals final potential plus final kinetic. Well, remember, I'm setting the point where I'm setting the point where they pass each other as my reference point. So initially they're separated by a distance of 2h. That means that M1 is at a height of h above the reference point. This is the initial. I'm looking at PE initial. M1 is initially at a height of h above the reference point. M2 is initially at a height of h below the reference point. So my PE initial is going to be M1GH minus M2GH. Just remember, this initially is this situation. The reference point is right where they meet, right, when they meet. So initially, M1 has a positive potential energy of M1GH. The potential energy of M2 is negative, minus M2GH. Now the initial kinetic energy is 0 because the system is released from rest. And obviously, if M1 and M2 are initially at rest, the pulley is initially at rest. Nothing complicated. So the initial kinetic energy is 0. Now let me set it equal to the final potential, or not let me set it equal, it is equal. PEI plus KEI equals PEF plus KEF. What's PEF? Well, PEF is 0 because, remember, I want to know V and omega at the point when they pass each other. Well, I'm setting that point right here. In other words, when they're at the same height, that's my reference point. So the final potential energy is 0 because they're both at the reference point. Okay. What's the final kinetic energy? Well, the final kinetic energy is the kinetic energy of M1, 1/2 M1 V squared, plus the kinetic energy of M2, 1/2 M2 V squared, plus the kinetic energy of the pulley, 1/2 I omega squared. Because remember, the final kinetic energy is the kinetic energy of M1 plus the kinetic energy of M2 plus the kinetic energy of the pulley. So my conservation of energy equation, PEI plus KEI equals PEF plus KEF, gives me this. M1GH minus M2GH equals 1/2 M1V squared plus 1/2 M2V squared plus 1/2 I omega squared. Now remember, I want V and omega. And when I say when I want translational speed, I mean V. Angular speed is omega. Well, when I say solve for V, you could just solve for V squared. It doesn't matter, and then just hit the square root thing. But so now remember, to solve for V, I need to write omega in terms of V. Well, remember, in general, V is r times omega. The tangential speed, the linear speed, V is r times omega. The linear speed, because remember, the linear speed as the string slides down the pulley, that linear speed is r times omega. It's okay, or omega is V over r. Okay, so first let me go ahead and take omega squared and replace it with v squared over r squared. Okay, so I have this equation, and then I take this equation, swap out omega squared for v squared over r squared, and then algebraically solve for v squared. And I get v squared is this expression. Okay? Or which means v is equal to this, you know, but that's fine. Now let me take this equation and let me let me pause for a second. Yeah, so what I did is I have my conservation of energy equation, then I want v, so I need to write omega in terms of v. Well, remember, in general, for a rotating object, the linear speed, the tangential or linear speed of a point on the object is r times omega, where r is the distance from the point, whatever point on the object, you want the linear speed of that point. R is the distance from that point to the rotation axis, to the pivot. But in general, v is r omega. So for this problem, the linear speed of a point on the edge of the pulley, that linear speed is big R times omega. So v is r omega, which means omega is v over r. So I take this expression for omega and plug it in right here. So omega squared is v squared over r squared. Then I go ahead and I take this equation right here and I solve it for v squared. That's why I just took this equation and just, pull out on the right hand side, you pull out the common factor of v squared, put it in parentheses, and divide both sides by that expression. You get this. Okay, that's v squared. What's omega squared? Well, if omega is v over r, omega squared is v squared over r squared, right here. Well, so then to get omega squared, I just take this expression. I take that expression for v squared and just divide it by r squared. And if you take this expression and divide it by r squared, you then are left with this. So and then you can stop with v squared or omega squared. Then if this is v squared, this is the expression for v, just put it under the radical. If this is omega squared, then what's omega? We'll just take that expression in the gray shaded area, just put it under the radical. But again, what I did is I took omega squared, put in v squared over r squared. This expression here, just this equation, solve it for v squared. You get this. Then once you have v squared, take your equation for v squared, divide it by r squared, and that gives you omega squared. So if you take this expression and divide it by r squared, you end up with this. And then, so that's that. So that's a conservation of energy approach. And it's somewhat easier because we don't have to worry about drawing the forces. It's just v, the linear speed v with that m1 is falling and m2 is rising with, that is the tangential speed of the edge of a point on the edge of the pulley. And that's v is equal to r omega, meaning omega is v over r. I'm going to go ahead and save this video and then we'll do angular momentum.